Hi, my name is Azaidis bin Azizi and my tick number is CD17078. This is the figure of the system. And now I will start with the stiffness of the neoprene, which is 350 Newton per mm. And this is the equation of the motion of the system. Before I start with the lowest natural frequency, I need to inverse the value of K and multiply with M and X. And I use the trial vector, which is 0.5 and 1. Here is the 5 iteration calculation before it converges, which is 0.691, and the natural frequency for the lowest is 45.61 radian per second. And now is the highest natural frequency calculation. I need to inverse the value of M first and multiply with K and X. It shows have a 7 iteration calculation before it converges, which is the value of 0.844, and the natural frequency for the highest is 110.736 radian per second. And now I go for the calculation for the mode shape. For the first mode shape, I got the value is 1 and 1.447, and second mode shape is 1 negative 0.217. And here is the graph for the first and second mode shape. Next, I will go for the stiffness of the solvaton, which is 600 Newton per mm. And I will start the calculation with the lowest natural frequency, and I need to inverse the value of K first and multiply with M and X. They have 5 iteration calculation before it converges, which is 0.691. And the natural frequency for the lowest is 59.719 radian per second. For the highest natural frequency, I need to inverse the value of M first and multiply with K and X. It shows they have a 7 iteration calculation before it converges to the value of 0.844, and the natural frequency for the highest is 144.988 radian per second. And I go for the mode shape. For the first mode shape, I got 1 and 1.447, and the second mode shape, I got 1 and negative 1.216. And here is the graph of the first and second mode shape. Thank you.
Hello, my name is Muhammad Nur Alif bin Muhammad Ali with metric number CD170163. Now, we go for the validation purpose. We use the MATLAB software and calculate the eigenvalue and eigenvector by using the power method solution. The program will compile and run, and we will get the value of eigenvalue and eigenvector. But first, we need to write the power method at the common space. This is the power method. For this case, I start the calculation of highest natural frequencies of neoprene. We need to calculate manually the value of subtraction of metric A and metric B. And then, after we get the value of subtraction of metric A and metric B, which is M inverse for metric A and K for the metric B, and we insert the value of subtraction here. And then we need to insert the trial vector. For this, our group choose to use 0.5 and 1. The program command will let the MATLAB know what to calculate. After finish, we now can compile and run the program. First, the power method will ask us to enter the dimension of the metric, which is n. N is, we need to insert the true value for the n, which is stand for 2 times 2 metric. Now we need to enter the tolerance. We enter the tolerance of this calculation is 0.6 0.001, which is 3 decimal places. And then the program will ask us to insert the iteration. We insert 10 for the iteration. This number of iteration only for the limit of the iteration and not the exact iteration to get the eigenvalue or eigenvector values. We now get the eigenvalue and the eigenvector. This value is same with the manual calculation, which is metric iteration method that we learned in chapter 5 of vibration. Now we go to the lowest frequencies. We also need to calculate the value of subtraction of metric A and metric B, which is represent the value of K inverse and M. After calculate the subtraction by using calculator, insert the value at A parts. And insert the same trial vector, which is 0.5 and 1. And now we can also run the program and insert the same number of n, which is 2, tolerance of 0.001, and maximum number of iteration, which is 10. And now we will get the eigenvalue and eigenvector. Eigenvalue and the eigenvector. This answer is same as the calculation by using manual, which is metric iteration method. This for the calculation of the second material, which is Soboton. We use the same command that used for the highest and lowest frequency of the neoprene. Only change the value of A. Thank you for listening for the validation part.
Hi, my name is Afiq Rahimi bin Sazali with metric number CD170187. I will present to you about the discussion for our project. So, from this case study, we use standard iteration matrix method to calculate natural frequency by using two different formula to find the lowest natural frequency and highest natural frequency. And the formula for the lowest and highest natural frequency are as shown. Next, when stiffness coefficient K for neoprene is equal to 350 Newton per millimeter, the matrix form are as shown. As you can see, the lowest natural frequency we get 45.61 radian per second, and the highest natural frequency we get 110.736 radian per second. Next, relative error for the lowest natural frequency are 67.42% and the highest natural frequency are 20.9. As you can see, they are a little bit different between the lowest and the highest natural frequency for the neoprene. We move to the next material. So, when stiffness coefficient K for Sobotron is equal to 600 Newton per millimeter, the matrix form are as shown. And for the lowest natural frequency and highest natural frequency, we get 59.719 radian per second, while highest is 144.988 radian per second. And for the lowest relative error is 57.34% and highest relative error are 3.56%. As you can see, they are still a little bit different between the lowest and highest, same as the neoprene. Next, we see the difference between mood shape for neoprene and Sobotron. The difference between mood shape and Sobotron are as shown. And as you can see again, there are two values, that is first mood shift and second mood shift. Thank you.